How's it going?
Good. So,
I was wondering the admin registration dates soon, so I was wondering if you have any ideas of what classes you might be teaching in spring yet.
I have no idea.
No clue?
The only one I'm relatively certain I'm teaching is a grad course, 540. The rest is kind of up in the air right now.
You know, the prereqs for the 540, but that count as a technical elective.
We can count as a tech elective, but usually, but you need basically you need to enroll within a 500 level course to be a permit. Um,
See the prereqs then.
you probably said usually our 500 level courses you probably have the prereqs for it, so it's on finite elements.
Okay.
Yeah.
Put it. Five, what, 40?
Yeah, 540. Yeah, we're gonna post more electives in the coming weeks. Right now, we don't have that many just because we're working on staffing for the required courses. And then we'll probably post. I'll probably teach one more tech elective next semester, but I'm just not sure where it's going to be.
And you're relatively certain I need a permit for that?
Yeah, because it's 500 level course.
Okay. All right, thank you.
Yeah.
When do they usually, I asked another teacher, he said about a month before the semester starts, that would, you know, or earlier, you think? Right.
Oh, you mean when more tech electives are
Well,
posted?
when you have your schedule for, so.
Probably end of the semester. Probably last week is usually. Yeah.
Okay, do you mind if I send you an email? Or
Sure.
I can also just walk in here.
Yeah.
I'm doing some tutoring, so it's like a minute away anyways.
Okay. Yeah, I mean, email or come
All right.
talk. Anything works.
Awesome. Thanks
Yep.
for letting me know.
Mm-hmm. Oh, let me change that. Yeah, you should be, if you just submit the MATLAB files, those are fine, but I need to probably update it to submit, .ems. If you want, you can turn the MATLAB files into PDFs too, so you can just publish it through MATLAB. But I'll change it when I get back to my office, so that it can accept M files too. Yeah, thanks for letting me know. Cool. All right, so it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Happy Halloween. Hopefully everyone's having a good time. I don't know if you guys still go trick or treating, but always good to get some candy. So hopefully that's you guys still can enjoy that. But if not, there's probably some Halloween parties probably going on. Hasn't been that long since I was a student, so I know how things are. Okay, so today is actually a pretty exciting day. So we are finishing up our 1D methods today. So I think we just had a little bit more to finish up with the quasi-Newton-Raphson method. So we'll go ahead and finish that up. I have an example for that. And then we're going to move on to multi-dimensional nonlinear programming. So in a lot of ways, these next few lectures, I would say the next 3 or 4 lectures are probably going to be the most important in the class because our multivariable nonlinear programming algorithms are going to form kind of the backbone of most of all the algorithms that we're going to cover from here. Okay. And so in fact, your final project is going to be a multivariable nonlinear programming type of problem. And so you're going to be implementing one or more of the methods that we're going to be going over the next couple weeks. Okay. And so with that, I am getting your guys' final project ready. I don't think I'll have it ready for next Tuesday, but let's talk about it next Thursday. So next Thursday, I believe that is November 6th. Let's talk about the final project on that day. Okay. So we'll talk about the requirements of the final project, what you need to do, what you need to code. Oh, all right, question in the chat. Yeah, so you guys will have to submit the MATLAB code. I need to change the settings on Canvas to allow for to accept MATLAB codes. So I'll do that after class today. Yeah. Yeah, so next Thursday, a week from today, let's talk about the final project. I need to make some modifications from the project from last year, so just to make sure that it's it's good. Okay. We'll talk about it then. So my plan for the final project is for you guys to have about a little bit over maybe a month and a half to work on it. So that's developing the code. There will be several optimization problems to work on for the final project. And writing the report. Okay. So the due date for the final project is not until December 22nd. So I believe it's the Sunday after finals week. So you guys have a bit of time. But now that we're starting to talk about kind of multivariable nonlinear programming algorithms, you can start to think about applying those towards the final project. So I think the timing is really nice to talk about it next Thursday, just because you'll have much better context about it after today's lecture and Tuesday's lecture. Okay. All right. That sounds good. All right. Any questions I can answer before we get started for today? Okay. All right. So let's pick up where we left off. All right. So I'm just going to scroll up for a second. So, you guys don't have to write any of this down just because it was kind of the end of the lecture last time. Okay. So last time we were here, we were talking about this idea of the Newton-Raphson method, which is kind of belongs to this class of methods called direct root. Okay. Okay. So kind of to motivate our discussion for direct root methods, we kind of went back to our discussion of our classical methods where, what we said was that the optimum of an objective function is just wherever the derivative is equal to 0. Okay. The problem is that, as our problems get more and more complicated, we get more and more design variables, we get our objective function gets more complex. It gets harder and harder to solve this equation algebraically. And so if you think back to our classical methods, problems that we did in the first half of class, most of the time I mostly just kind of gave you guys polynomial problems, which are convenient, but also are not super realistic too. So we have a lot of objective functions that don't really follow polynomials. And also, there's a huge class of methods where the design variables don't show up in the objective function either. Okay. And so, the whole idea with direct root methods is to help us solve this problem using an alternative means. Okay. And the main method that we are using is called the Newton-Raphson method. It's a very famous method used in lots of different fields of computational science. And it's a very simple recurrence relationship. Okay. And so basically the idea with Newton-Raphson is that it's an iterative method. And so it's something that you have to kind of repeat over and over and over again. And so basically the way the method works is that you start with an initial guess, and then your next guess or the next step in the algorithm is determined by this formula here. Okay. So x at I plus 1, which means your next guess is equal to xi, the current guess, minus f prime of xi divided by f double prime of xi. Okay. So we did an example of that. So we show that this method works. Okay. But there was one problem, right? So the problem being that in order to use this recurrence relationship, we have to actually take the derivatives of our objective function, okay? Which kind of violates all of our rules that we were kind of imposing ourselves in this whole unit, right? So the way we're getting around that is that instead of computing these analytically, right? Instead of computing the first derivative and the second derivative, by computing it normally by derivatives, what we can do instead is we can approximate these using finite differences. And the benefit of using finite differences is that, finite differences, you can approximate the derivative using only function evaluation, which is really good. That's what we want, okay? And so what we said last time is that based on our understanding of how derivatives are derived, and based on, numerical theory that we're kind of, skipping over a little bit just in favor of time, we have these two expressions here for the first derivative. So up top, the first box equation is, the finite difference approximation of the first derivative that only depends on the function evaluations. And on the second box right there, we have the finite difference approximation of the second derivative that again only depend on function evaluations. Okay. So let's take these two expressions and plug them into our Newton-Raphson recurrence relation to get the quasi-Newton-Raphson relationship. Okay, this is quasi-Newton-Raphson. Okay. And so if we plug in the finite difference approximations for f prime and f double prime, okay, we're plugging this into the recurrence relation. Okay. So I'm going to skip the algebra. I assume that you guys can kind of plug in for the algebra. We get this new recurrence relationship which looks bigger, which looks scarier, but you'll see that we no longer explicitly depend on the derivatives. We can compute this just from some clever function evaluations. Okay? All right. All right. So once again, we have an equation for xi plus 1. This is equal to xi, okay, minus. And so when you plug in those relationships, we have a factor of delta x that gets canceled out. Okay. And so out in front here, we have a delta x divided by 2, okay, multiplied by f of xi plus delta x minus f of xi minus delta x, all divided by f of xi plus delta x minus 2 f of xi plus f of xi minus delta x. Okay. So that right there is the quasi-Newton-Raphson relationship for how to get the next guess in our Newton-Raphson iteration. Okay. So the quasi-Newton-Raphson method, the algorithm is exactly the same. So I'm not going to write it down again. It's the same as above. But instead of using the original, the original recurrence relationship, we're using this one instead. Okay. Now, of course, in order to use this method, we have to define our grid spacing here, or our step size. So that's an additional parameter that we have to set. And usually, in most finite difference approximations, we choose this delta x to be something somewhat small. There's a lot of theory in terms of, how do you choose a step size for a finite difference approximation. But for our purposes, you just make sure that it's something small. All right. So I'm putting small in quotation marks there because small is relative to your problem. So 0.1 might be small for one problem, but it might be very large for another problem. So some of it you kind of just have to use some intuition. But if you're not sure, then using something, just using a denominative value like maybe 0.01 is usually pretty good. Okay. You want it to be small enough so that the derivative that you compute is accurate. But you don't want it to be so small, let's say if your objective function is slow varying, so it doesn't really change all that much with x, you may have to choose a larger value of delta x in order to compute your derivatives more accurately. Okay. So you start after you do this for a long time, you start to get some intuition. But if you're not sure, then just kind of start with something. I'll give you. I kind of hesitate because I don't like to give default values for something like this because it really depends on the situation. But you always have to start somewhere, right? And you don't really build intuition unless you actually try to use it. So maybe something like 0.01 is not a bad starting point. Okay. Any questions on this? Okay, so let's do an example. And so this one I'm going to primarily do it in code, just so you can see. It's a very short code. You'll see in a second. Right? It's definitely conceptually much simpler than our interpolation methods. But first, let me give you the objective function. Okay, so we're going to find the minimum. And our f of x here actually is the exact same as our last one. So it's going to be 0.65 minus 0.75 divided by 1 plus x squared minus 0.65x tan inverse of 1 over x. Okay, so once again, we have this kind of monstrosity of an objective function. Last time we did this example with traditional Newton-Raphson, we took its derivatives, but today we say, we're done with that. No more calculus. Let's use quasi-Newton-Raphson. Okay. So I'm not going to do this one by hand. It would just honestly just be a repeat of kind of what we did last time. So instead, let's look at the code. Just so you can see how this method is implemented in code. And so the code that I have for you is example 5. I believe let me see the exact name of the code. I posted on Canvas as well. So the name of the code is 1D _NLP underscore example 5, okay. Quasi-Newton dot F. Okay. So, this code is posted on Canvas for you to see, but, we're going to look at it right now. Okay. All right. So let me go ahead and share my screen here so you can see what I'm looking at. Okay. All right. So here is our code. So if you have trouble locating it, this is our Canvas site right here. So you would go to this week, and you'll see that I posted the code 1D NLP example 5 quasi-Newton. Okay, so it's one of the example codes that I've had here. You can also go to the files folder, go to code examples, and you'll see it here as well. Okay, along with all the other code that we're going to go over in the class. You'll see that once we get to unconstrained nonlinear programming, there's a lot for us to do. Okay, but we're going to start with this one here, 1D NLP example 5. Okay. All right, so you can see it's a fairly short code, so it's only about 42 lines right here. Okay. Let's go ahead and go through it. Okay. So first thing, let's go back to, if you look back in your notes in terms of how the Newton-Raphson method works, first thing you need to have your initial guess. Okay. So X naught here is the initial guess for our op. Okay. So most of these methods, you need to start somewhere. And so, that is our first guess here. Okay. Okay. DX. So DX here, this is our step size. Okay. So that was the delta X variable that we just kind of finished talking about just 5 minutes ago. And so you can see here that I've set it to be a value of 0.01. So, for this problem, I know just how much it varies. And so I know 0.01 is a good step size for that. Okay. Okay. And another thing that we have here is we set our convergence tolerance. Okay. And so if you remember this from the example last time, we have to terminate the algorithm at some point. Because if you don't terminate it, then it's just going to keep iterating forever. Okay. And if you remember, the criteria that we use to terminate the algorithm is when our first derivative at our current guess is close to 0. Okay. So this is the threshold for terminating the algorithm when the magnitude of f prime is less than this, then we stop. Okay. So, when you're doing numerical stuff, it's really hard to get something that equals exactly 0. I mean, ideally, we use this algorithm until we hit the optimum right on the nose, and our derivative is precisely 0. But in numerics, it's very hard to do that just because of how just because of the computer precision is so high. And so oftentimes, instead of setting something or instead of checking if something's equal to 0, what we do instead is that if it's close to 0, if it's less than some tolerance, then we can go down. Okay. Okay. All right. So another thing that I have here is I'm introducing this concept of a built-in function. Okay. Or excuse me, a user-defined function. Right. So this is something we haven't used before. So I wanted to kind of take the time to introduce it to you. Okay. And so a built-in function is a great way for you to evaluate your objective function. Okay. Because if you think back to our previous codes, and so, in fact, I have one pulled up right here, right? There's a lot of times in the code where we have to evaluate our objective function. And so you can see here for quadratic interpolation, we're evaluating the objective function 3 times, okay? And that can get pretty cumbersome, especially for our multivariable cases, which are going to rely on lots and lots of different variables, right? And so one way to kind of make your code a little bit more, reader friendly, because you're going to be repeating this code over and over again, is to define what's called a user-defined function. Okay. And so the way it works is like this. And so any user-defined function you have to put at the end of your code. Okay. And we have one here for computing the objective function, okay? And so the way it works is like this. And so you use a keyword called function, okay? And so that tells MATLAB that you're defining your own function. And then you define the output of the function. So this is what the function is going to return. And then you define the name of the function here, okay? And then you define the inputs of the function right here, okay? So that's three, it's a small amount of space here, but there are kind of three key things here. So again, you have to have the outputs, and then the output is kind of what you are referring to on the inside. You have the name of the function itself. So that's what you're going to call later on in your code. And then you have the input variable right here, okay? Okay. And so the way the function works is that, once you're inside here, you can define, you can do kind of anything that you want with the input here, okay? And so since here we just want to evaluate the objective function, and so what we say is that the output eval, notice how this eval matches the same thing as this eval right here, okay? So these two are the same. And then this equals to, and you can see here that we've input our objective function for this problem. So our objective function for this problem is 0.65 minus 0.5 divided by 1 plus x squared minus 0.65 times x times arctan of 1 over x, okay? Okay, so since we're going to be computing this function over and over again, I just defined a user-defined function here. And so now whenever we call this function, and so, for instance, let's look at line 13 of this code right here, okay? And so in line 13 of this code, you can see that I am calling my feval function. And what I'm plugging in there is I'm plugging in the initial guess, okay? So I'm saying feval evaluated at x is equal to x naught here. And so this f here is going to be basically our initial objective function evaluation, okay? So from here on out, you're going to see me use user-defined functions more and more in our MATLAB codes. At this point, it's pretty much, it's fairly optional. If you don't feel comfortable using user-defined functions, you can kind of ignore them for now. And so one other way that you can do this is that instead of doing this here, you just plug in the objective function up here. So whatever the objective function is, you just plug it right in here, okay? And then everywhere you see x, you plug in x naught, because that's where you want to evaluate, okay? So this is exactly the same as the line that we had previously with the user-defined function. It's just the user-defined function makes it a little bit cleaner, especially when you're doing finite difference approximations, where you're doing slight modifications to the input. Okay. Okay. And so another reason I like user-defined functions here is that this finite difference approximation looks very similar to how we have it in our notes, right? And so the finite difference approximation for the first derivative is f of x plus dx minus f of x minus dx, all divided by 2 times delta x, right? And so this looks pretty much like we have in the notes. And so, we've substituted the objective function with our user-defined function here, which just simply computes it right there, okay? So the beauty of using user-defined functions here is that you can feed it a slightly different value, and it's going to plug that into your objective function for you, okay? So you don't have to kind of fuss around. So you can imagine if we just put in the raw objective function up here, it's going to make this line of code look really, really messy. So we use the user-defined function here to kind of clean it up. Okay? Same thing for the finite difference approximation for the second order derivative. So we can see here we have our user-defined function, x plus dx minus 2 times f of x plus f of x minus dx divided by delta x squared, okay? All right, so that is our initial guess. So that's our initial guess for our function evaluation for the first derivative and initial guess for the second derivative, all of them computed at our initial point, x naught is equal to 0.1. Okay. Any questions on how we set up that user-defined function? Okay. Have you guys seen user-defined functions before in like 205 before? Okay. Okay, so you guys have seen it before. It's just, but yeah, in optimization, it's a godsend. You'll see, especially when you're doing your final project. You don't want to be plugging in your objective function in your final project code. Okay, and so from here we enter into the recurrence relationship, right? Okay, so once again, you see another while loop here. And so we say while our first derivative here, df, as long as that's greater than our convergence tolerance. And so in other words, we're at a point where our derivative is not close to zero, then we're going to update our guess. Okay. All right. So next thing we have our recurrence relationship here. So you can see it's just one very simple formula. So we could say that we're going to update the value for x guess. And we're going to update it by subtracting the first derivative divided by the second derivative. Okay. Those things that we computed earlier, right? And then after we do that, then we have to update since our value for our guess has changed, we have to recompute the value of our objective function, the first derivative, and the second derivative. Okay, so you can see these three lines of code are actually identical to these three lines up here. Okay, and so the only difference is that our value for x guess has changed because we've updated it within the loop itself. Okay, and this just kind of repeats itself until we reach convergence. Okay. Okay, so I'm going to go ahead and run the code, and then once this code is done, it's just going to tell us the optimum from there. Okay. Okay, and so we run the code, and what we see is that the optimum is located at x is equal to 0.48. And so if you look back at our example from last time, you'll see that that's exactly what the optimum was. Okay, so quasi-Newton-Raphson, very effective way to compute optimums there, and we didn't have to compute a single derivative. So instead, remember, we're approximating our derivatives with the finite difference approximations, which only rely on the function evaluations. All right, any questions on this code here? Okay, good. All right, so again, simple code, definitely check this one out. This one I think is much easier to read. You'll see that I have another example code here for the regular Newton-Raphson method. So we didn't go over this code just because we worked this one out by hand. But make sure you kind of check this one out as well. Okay. All right, so let me go ahead and bring back the iPad. All right, and so that will do it for our 1D methods. And so, we've spent quite a bit of time on this, and so I believe it was about 4 lectures on 1D nonlinear programming methods. But I really wanted to take my time with this section here, just because it kind of represents a big paradigm shift in the class, right? We've gone from first half of the class where we're computing these optimums by hand. Now instead we're defining these algorithms for a computer to find them for us. Okay. So of course, we've worked out a few of these algorithms by hand. We've done the calculations just because we can do it in 1D. But now that we're moving on to multi-dimensional problems, the amount of calculations that we can do by hand is going to be very, very limited, if not impossible. And so from here on out, it's going to be just all MATLAB. So the lectures, from here on out are going to consist of me just kind of describing the methods. Describing the algorithm, just using words, but we're not actually going to do any calculations ourselves in the notes here. And so it's going to be just kind of flip-flop between notes, describing the algorithm, describe the logic, describe kind of the strategy and how it works, and then going straight into the MATLAB code and seeing how it's implemented. Okay. So from here on out, you guys, it really pays to be kind of really comfortable with MATLAB. Because otherwise, it's going to be a big jump to go from the logic on the paper to how it's implemented in the code. So if you're still kind of feeling uneasy with the MATLAB, definitely let me know. And maybe we'll do some additional examples in class, or maybe I can help you on the office hours. And so the class kind of ramps up from here, even though it's kind of it feels like it's been ramping up a lot. I know, but from here, it's going to be all MATLAB, all the training wheels are off. That's one way to kind of think about it. Okay. Okay. All right. So let's go ahead and start. Okay. So this next big unit, and again, I expect us to kind of be in this unit for probably the next 3 or 4 lectures at least. is what I call unconstrained multivariable nonlinear program. Okay. This is kind of the meat and potatoes of this class. And so, but the exciting thing is that, a lot of the methods that we're going to go over in this section are very much modern methods. People actually use these methods today to optimize their designs or optimize their math problems. And so, this is pretty much, state of the art right now. So, okay. All right. So let's kind of recap kind of the key points from our 1D section, right? So from the 1D nonlinear programming, we kind of picked up a few key points, right? Okay. So the first key point is that, the whole idea with nonlinear programming is that we want to get away from relying on derivatives to compute our optimums. Another way to put that is that, we want to be able to compute optimums using only function evaluations. Okay. And the reason for that, and you'll see that more and more, over the coming weeks, that sometimes computing derivatives of your objective function is literally impossible. Okay. So that's kind of the main point. And so, we want methods or we want algorithms that can do this. Okay. The second key point is that, restricting ourselves to this, to find methods that can only work when you evaluate function evaluation, these problems are very difficult to do by hand, again, if not impossible. Okay. So we really need computers to kind of, give us the computing power to do all the calculations that are needed. Okay. And the reason for that is that all of these algorithms are iterative in nature. So you need to repeat it, hundreds, thousands, if not millions of times. Okay. Okay. And the third key point, to put it in very layman's terms, that there's a lot of different ways to skin a cat. And so, maybe something that you've wondered over the last, 3 or 4 lectures is that, there's so many different methods for doing this, but they all do the same thing, or they all kind of arrive at the same conclusion, right? Their goal for every method is the same, to compute an optimum solution. But, we went through exhaustive search, we went through dichotomous search, we went through interpolation methods, Newton-Raphson, quasi-Newton-Raphson, right? So all of them, they're all very interesting in the way that they're implemented. And so if you're kind of an algorithm geek like myself, then, you find it interesting to do. But, at the same time, if you have a problem, you're only going to use one method unless you're kind of a nerd like me. And so the question then becomes, as we start to learn more and more algorithms, which one is best, or which one do we use in certain situations? And so the truth of that is that, in certain situations, some methods are going to be good than others. And so another thing that we're going to start to recognize over the next few weeks is, what are some of the situations where one method is good for another? Okay. Another thing that I want you to think about over the coming weeks that, I didn't really bring this up in the previous unit, but, it's actually even possible to combine some methods as well. Right? Because again, some methods are going to be good in some situations, and some methods are going to be good in other situations. Okay. And so, sometimes it's best, why don't we take the best of both worlds? So why don't we, use one method to get us to a certain point, and then we use another method to, take us to another point. Okay. All right. So those are, the kind of the three key takeaways from the 1D nonlinear programming, or at least from all the algorithms that we've gone over so far. Okay. All right, but of course, we're making things a bit more complicated now. So we're working in multiple dimensions. Okay. So when you have multiple design variables, even just going from 1 to 2, your problem will increase in complexity pretty much exponentially, right? So every time you add a design variable, it's going to become more and more complicated. Okay. Because one thing you have to think about when you have multiple design variables is you have to think about the dependencies between the design variables as well. Okay. And what I mean by dependencies is that, maybe, so one approach that we'll talk about later called coordinate search is, coordinate search aims to optimize kind of one variable at a time. So you basically take a one-dimensional method, something that we've done before, and you just apply it to your objective function to optimize one design variable at a time, right? So you optimize one variable, then you optimize another variable, then you optimize the third one, and the fourth one, and then the fifth one, right? And so on and so forth, right? And so by that logic, if you optimize one at a time, then, most people would think, like, oh, this is our true optimum here. But maybe, every time you change one of the design variables, you change the objective function for the other ones as well. So maybe you find an optimum for one variable, but as soon as you change another one of the variables, suddenly that first variable is not in its optimal place anymore, right? And so when you have multiple levers to turn, it becomes a lot more complicated, and you have to kind of think about that, as you are kind of designing your algorithms here. Okay. So there's a lot to think about, and and the methods that we're going to go over, it may seem, they may seem straightforward in hindsight, as we're kind of describing them in the class, but these methods were not obtained very lightly too. So there was a lot of development that went through them, because just getting an algorithm that works in multiple dimensions is actually a pretty big. All right. All right, so before we get to our first algorithm, I did want to revisit the concept of conversions. So let's talk about that before we go to our first algorithm. Okay. So rate of convergence. Okay. So, we talked about this briefly before about, what makes a good optimization algorithm, right? So, so the first algorithm we talked about was exhaustive search, but we said that that's not a very good method. In fact, it's probably one of the worst methods out there. So what makes, interpolation method, what makes quasi-Newton maps, and what makes it better than exhaustive search? Right? And so remember, a good optimization algorithm will reach the optimum solution it'll reach the optimal solution in the least amount of function evaluations possible. Okay. So if you have one optimization algorithm that gets the optimum in 1,000 evaluations, and you have another one that gets it done in 100, the 100 ones are going to be more, more desirable. Okay. All right. And the reason for this is that, usually when you evaluate the objective function, that comes with some cost. So, it's something that's a little bit hard to appreciate in this class just because, I'm not giving you costly objective functions. But sometimes just one function evaluation for an objective function can take up to, an hour, right? And so if you have an algorithm that takes, 1,000 iterations to complete, that's 1,000 hours that you have to wait versus waiting 100 hours. There's a big difference between those two. Okay. So when we say that a particular algorithm has a good rate of convergence, what that means is that it arrives at the solution in an efficient amount of time. Okay. So there's a way that we can quantify this, right? And so the way that we quantify is that we take the absolute value of xi plus 1. Remember, we have x vector now because we're in a multidimensional case, minus x star. X star here is the optimal solution divided by xi minus x star is less than or equal to some convergence threshold. All right, so epsilon here, this is the convergence threshold. X star here is the optimal solution. Okay. In some cases, X star, for this expression explicitly, the optimal solution is something that's theoretical, right? So sometimes, a lot of times you don't know the optimal solution beforehand. This is just an expression of, how quickly it converges, okay? And then xi and xi plus 1, these are two subsequent guesses of the algorithm. Okay. So what this expression here is basically saying is that, as you go through successive evaluations, or successive iterations here, xi plus 1 is going to be closer to the optimal solution than xi, right? And so even just plainly speaking, just for convergence, that expression on the left-hand side there should be less than 0 or less than 1, excuse me. Because if you take the difference between your second guess versus your third guess, your second guess, that difference there should be smaller because you're getting closer to the optimal. Okay. And so if your algorithm here has this thing greater than 1, then you have a problem because then your algorithm is getting actually further away from the optimum rather than closer. Okay. Now the key here, right? So any good algorithm should have this be less than 1, right? But there are some cases that approach 0 faster than others. Okay. And so that's what we call the rate of convergence. And so, that was kind of fast. And so, in case you didn't catch it, right? There's actually a key parameter here, P, that is kind of an exponent of the denominator. Okay. And that P here is what we define as the rate of convergence. Okay. All right, so remember, we want this expression, this fraction here to go to 0. And so a faster way for it to go to 0 is if P is greater. Okay, so higher P means better method, faster convergence. And so in order just to be a valid method itself, the P has to be at least 1 for your method to be valid. So P equals 1 is the minimum. For a viable method. Okay. And the way that convergence rates are usually talked about is that they're usually talked about in terms of polynomials. So P equals 1 here, what we say is that is linear convergence. If we have P is equal to 2, that's quadratic convergence. Okay. Okay. P equal 2 is better, and this is quadratic. Okay. Most methods are going to be somewhere between 1 and 2. Quadratic convergence is actually really, really good. If you can achieve quadratic convergence, that's excellent. And so if you can get your algorithm to get higher than 2, like 2.1, 2.2, 2.3, you're in kind of really excellent territory. Now there's certain methods that if you give it a very specific situation, you may get super convergence. So we'll talk about that a bit later, but that's very rare. So most of the time for a general problem, your general convergence is going to be somewhere between 1 and 2. All right, any questions on this convergence expression here? Okay, so this exact expression is not that important. So we're not actually going to compute this. The important part here is more this terminology. And so I'm going to bring up algorithms over the next couple weeks. And so I'm going to say this method here is linearly convergent, or this method is quadratically convergent, or this convergence is like 1.2, 1.3. And so just so you know just how I'm talking about this. Okay. Okay. And so that's kind of enough, enough kind of introductory information. Let's get into our first algorithm. Okay. Okay. So the first algorithm I think has the coolest name, but it's also the dumbest method in the world. But it's a really dumb method, but it's actually very effective. So it's called Monte Carlo methods, or the Monte Carlo method, I should say. Okay. So it's kind of tradition in the optimization community. Once you kind of start talking about multivariable and nonlinear programming, Monte Carlo is kind of the first method that you it's pretty much universally agreed upon. So let's talk about the name first. a little bit of trivia. So if you don't know Monte Carlo, Monte Carlo is this very famous kind of French resort town in the French Riviera, or no, it's in France, kind of south of France. That's very famous for gambling. So if you're a fan of James Bond movies, you've seen it in the film Casino Royale. So that very really nice town that Daniel Craig goes to, gamble, and it's a super high stakes poker game. That's kind of the climax of the movie. That's where Monte Carlo is. Okay. And so this method here kind of takes inspiration from that idea of gambling. Okay. Monte Carlo, unfortunately, Las Vegas was created, after Monte Carlo, and so, I think if Las Vegas was done sooner, maybe this method would be called the Las Vegas method. But Monte Carlo was made first, so that's why we call it the Monte Carlo. Okay. Okay, so how does it work? I can sum up Monte Carlo method in just one sentence. Monte Carlo method is just do random shit until you find the optimal. Okay? For the notes, I wrote it in a little bit more PG terms, but that's it. That's it basically. And surprisingly, this is a convergent method, right? So it's the lowest convergent. So technically, it's a linearly convergent. Okay, but it works, and it's sometimes for certain problems that are super complex, sometimes Monte Carlo is kind of the best that you can do because some of the other algorithms are just not going to perform that well. Okay. Okay. So this method here, even though it seems very simple here, it gets around one of the primary difficulties of working in multivariable space, which is the dependencies. Okay. Okay. So you'll see later on that, all the other methods are sequential in nature, and so your next guess is going to depend on your current one, very much like the Newton-Raphson method. But with Monte Carlo method, you're kind of just doing just kind of guessing randomly. So you're just kind of jumping all over the domain. And so, when you have a problem with very complex dependencies between the design variables, Monte Carlo actually is not a bad idea, especially at least to kind of start you out. Okay. So since this method jumps around, okay. And so you'll see that another difficulty that some of the more sophisticated algorithms get into is that sometimes they can kind of get stuck in a particular area. Monte Carlo kind of breaks this. So Monte Carlo actually will jump around so that you can kind of, don't really get stuck and you don't really get bogged down by the dependencies. Okay. All right. So let me illustrate this for you. So I'm going to illustrate this with 2D. All right, so for a lot of the algorithms that we're going to talk about over the next couple of weeks, I'm going to illustrate it using a 2D problem just because it's easy for me to draw. But just know that these methods are not limited to just 2D. So you can work with them in 3D, 4D, 5D, as many dimensions or as many design variables as you can. Okay. Okay, so these plots are back. So these plots we haven't seen since the beginning of class. Okay. So we have a design space here where each of the axes are defined by our design values of our design variables. Okay, so x1 and x2. Right. So if you recall, from the early parts of the class, a lot of times we'll be given a certain region where these, where we can define valid values for the design variables. Okay. Okay. All right, so the way Monte Carlo works is that we're essentially going to be jumping around this domain into random locations. So we're going to choose a random variable for a random value for x1. We're going to choose a random value for x2. We want to make sure that it's within this valid region. So that's kind of the important thing. And we're just going to evaluate the objective function at each location. Okay. So let's say that we start here. Okay? So let's say this is point A. And so we get x1, x2 evaluated at point A. Okay. All right. And so at this point, we're going to evaluate the objective function. So we're going to get evaluate x1a, x2a. Okay. And then we save, right? So that's our first guess. And so we just save the objective function value there. Okay. All right. Next step. So next step, we've evaluated that. We say, all right, that's cool. Let's jump to somewhere else. And so let's say we jump here. Okay. So this would be point B. Okay. And it's from here, we're going to compute, or we're going to evaluate x1b, x2b. Okay. So two different values for our objective function. And then we compute f of x1b, x2b. Okay, so now we have two guesses, right? And so now, but now we have to make a decision, right? We have to decide which one of these is better, right? So at this point, we're going to compare, right? So we're going to compare f of x1 at A and x2 at point A versus f of x1 at B, x2 at B. Because what's likely going to happen is that one of these locations is going to be more optimal than the other one. Okay. And so if we're doing a minimization problem, then we're going to choose the one that has a more minimum value. If we're doing a maximization, we choose the one that's more maximum. Okay. So let's say for the sake of argument here that let's say that our initial point was more optimal. Okay. We're going to assume this is more optimal. Okay. Right, and so if our first guess is more optimal, then we say that, all right, location B, that was a failure. And so we just say that, all right, we're just going to forget about that. And then we're going to jump to a new location. So let's say that we jump here, okay? And so we have point C. Once again, we're going to evaluate the design variables here. So x1c, x2c, and then the objective function as well. F of x1c, x2c, okay? And then we do a comparison once again. And so, basically the idea is that, you're just going to jump to random places in the domain. Every time you make a new guess, you're going to see if that new guess is better than your previous best. If it is, then you save that new one. If not, then you just keep the old one and you just keep repeating this over and over and over. Okay. And by the power of large numbers, the power of the power of the computer, eventually, you guess enough and you're going to get an optimal solution. Okay, so all right, so that's kind of the idea with Monte Carlo. I'm going to write out kind of the exact steps of the algorithm in a second, but are there any questions on kind of how this works here? Yeah.
Does it all say that never repeat stuff, or is it just fully random?
It's just fully random. Okay. Yeah. It's actually very, very rare that you're going to get two of the exact same points. You may get very close, but but sometimes that's good too, because sometimes maybe sometimes you're kind of really warm but you're not quite at that maximum yet, so maybe you want to check something that's close to it. Yeah. Especially once you get to higher dimensionalities like 3D, 4D, 5D, it's very rare that you check the same. Okay, so let's write out the algorithm. Okay. So step one. So before we start, so even though I've kind of been describing Monte Carlo as this kind of chaotic thing, there are some rules here, right? So you just can't guess truly random values. You have to place some limitations. Right? So for each step one here is that for each of your design variables, okay, what you need to do first is you need to define the maximum allowable value and the lower allowable value. So the upper bound and the lower bound. Okay. And so what that does is that, Monte Carlo will basically just, when it guesses randomly, it'll guess something between the upper bound and the lower bound for that variable. Okay. This is to kind of save you from the method guessing, 1 billion and negative gajillion for your variable, right? So you have to kind of constrain it a little. Okay. All right, step two. Step two is to take your initial random guess. Okay. And so you're going to take a random guess for every single one of your objective or every single one of your design variables. Okay. So how do you do that? Oh, question.
Would that be something you do, or you just tell a computer?
You tell computer to do it. So there's a function in MATLAB that you can do to generate a random. Yeah. In fact, here's kind of how you do it. And so the formula to compute a random number in MATLAB, well, there's a function in MATLAB called rand. Every programming language has its own way to generate random variables. And so what this does is that this generates a random variable between 0 and 1. Okay. So it's going to be some decimal. It's probably going to be 0 point something. Okay. And it's red, right? If you want to get into randomness, it's actually really hard to recreate true randomness in computers because a computer is not really a random device. It's a very much, it follows its instructions. So the way random numbers are actually generated in code is that usually it just takes it honestly sometimes it just takes kind of random bits of memory in your computer and then uses that to compute a random number. Sometimes it uses just a particularly chaotic function like maybe sine some sinusoid that's just really, really chaotic with a with a frequency. So you can actually manipulate the random variables a little bit. But for our purposes, you can consider it to be kind of a true random number. Okay? So the way to generate a random variable for x, right? So most of the time, our design variables are not going to be between 0 and 1. They're going to be, have some lower bound and upper bound. So to generate a random guess for a variable xi, okay, you're going to take its lower bound. Okay. To that, you're going to add rand. Okay, so that's the random component multiplied by ui, where ui here is the upper bound for that variable, minus li. Okay. All right, so this will generate a value for xi that's between its lower bound and upper bound. Okay. Okay, so we're gonna do this for all the design variables. Three, after you evaluate your initial random guess, you're gonna evaluate the objective function at that guess. Okay. So there is our objective function, okay? And since this is our initial guess, we're gonna save this as our best guess, okay? So you're gonna have to create another variable to keep track of your current best guess. Okay. Step four. Step four is to generate another random guess. Okay. So you're gonna use the random function again to compute the next guess, and you're gonna evaluate the objective function at this location. Okay. All right, step five. Step five is our comparison step. Okay. So now that we have at least two random guesses, we're gonna compare. So we're gonna compare our most recent guess to our previous best guess. And so if our new guess, if it's better, save. Okay. If not, toss it. Okay. All right, so there's an if statement that has to go there, right? So after you generate your new variable, your new design variable, if you test it, if it's better, then you save that location. If not, then you toss it and you generate the next. Okay. So the last step in the algorithm is just to return to step four. And repeat. And so you just basically just keep doing this until you have to stop at some point. Okay. And so in theory, there's actually no convergence of Monte Carlo. So there's no point where you can stop it prematurely. So usually with Monte Carlo, you're just repeating it for a set amount of times. And so you're basically deciding beforehand that you're going to generate 10,000 guesses, and you're going to find the best one out of that 10,000. Okay. All right. Any questions on the algorithm here? Okay. All right, so last thing I want to do today is I want to show you the code for this, and then we'll wrap up for today. It's kind of a good stopping point. Okay. All right, so let's optimize the following function. So I'm going to give you a two-dimensional function here. So it's going to be a function of x1 and x2. This is equal to x1 minus x2 plus 2x1 squared plus 2x1 x2 plus x2 squared. Okay, and so we want to optimize this using Monte Carlo, but clearly, we can't do this by hand, just because, you can try to generate random numbers in your head, but it's not going to be as random as the computer, right? Okay. So let's use, let's say both variables have an upper and lower bound of -2 to 2. Okay, so we're going to search in that range and find the best variable for this. Okay. All right, and so from here, I'm going to switch to MATLAB. Okay. And we'll go through this. Okay. All right, any questions on this before we switch to MATLAB here? Okay, all right, so let me go ahead and switch to MATLAB here. Let me go ahead and share my screen once again. Okay, so once again, these codes here are posted online, and so we're going over the first one here. We're doing UNLP example 1 Monte Carlo. Okay, so I believe I have it downloaded already. Yes. Okay, so you can see here fairly short code, just about 40 lines, but here we go. Okay, all right. So, first thing that we're doing here is we're defining the number of iterations. So, you can kind of go crazy with this if you want, right? Because remember, we're doing this in the computer. And if your objective function here is just a simple polynomial, these are very, very cheap to compute. Okay? And so here I'm computing it, let's see, 90 million times. Wow, okay, that's kind of a lot. Okay, so we're doing 90 million iterative guesses here, and we're going to find the best guess out of that 90 million. Okay, now do you need 90 million guesses for only 2 variables? Probably not, but I guess I'll just kind of feel in myself and just say why not? Okay, so you can see here that we have the upper and lower bounds here, right? Looks like in this program here, I also have an initial guess. So you can do this too. So you can start it out with the point of your choosing. Or you can just let the randomness kind of take over as well, okay? Okay, so you can see here that we've defined the upper and lower bounds for x1 and x2 to be -2 to 2, okay? And then we enter into the loop right here. Okay, all right, so you can see here that we have a for loop, right? So because, we have to run this for a fixed amount of iterations, then a for loop makes sense here, okay? First thing we're doing inside the for loop is we're generating random variables. We say R1 is equal to rand, R2 is equal to rand, okay? You can include the parentheses if you want, but but MATLAB knows that if you just do rand by itself, it's going to compute a random variable. All right, next thing you're going to do is you're going to compute your guess for x1 and x2. So you're going to say x1 trial is equal to its lower bound plus the random variable multiplied by the difference between the upper bound and the lower bound, okay? We do that for both x1, x2. And then after you generate your guess, you can see here that we're computing the objective function at this point, okay? All right, so now that we have our trial point, we have our current best point up here. Next, we have to compare. And so if this trial point is more optimal than our best point here, then we're going to save it. And so if we save it, then we save our current value for x1, x2, and we save our current value for f best, okay? And then we just do the whole thing over again. And so we just kind of repeat this over and over, okay? All right, so let's go ahead and run it. So you can see here with 90 million guesses, it takes a little bit of time, okay? All right, and so with that, we're able to obtain the optimal values for x1. So you can see the optimal value for x1 is about -1, and the optimal value for x2 is about 1.5, okay? All right. So that's Monte Carlo in a nutshell. So, you may be asking yourself, how does Monte Carlo compare with exhaustive search? Believe it or not, Monte Carlo is actually more efficient than exhaustive search, especially when you get into the multidimensional case, right? Remember, exhaustive search means to check everything between, your upper and lower bound. And so if we were to do this with exhaustive search, it would look like kind of a nested for loop, okay? which, for 2 dimensions, maybe is not so bad, but, if you have a 5-dimensional problem, you have a for loop that's kind of 5 layers deep. And then, you're just kind of screwed at that point. So, for higher dimensional problems, actually Monte Carlo it performs much better than exhaustive search. Okay. And again, Monte Carlo is not bad. The only thing is that, you're limited by randomness and, it takes a lot of iterations to kind of get there, but you can see that it works clearly. So it's not a bad method. It's just very kind of barbaric. That's the kind of phrase that we say. People say Monte Carlo is just kind of brute force and computer. Okay. All right, any final questions on this? Okay, all right, so when we come back on Tuesday, we'll talk about our next method. So our next method is called random walk. So a little bit similar to Monte Carlo in that we're going to rely on randomness, but just how we incorporate that randomness is going to be a bit different. Okay? All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Tuesday.
So I was looking at my results, I was wondering if I can go. Yeah. So I went with a grip handle for a push scenario.
Yep.
I explained the basic information and then I did the normal stress to describe like the tensile and compressive stress. And then my other scenario was a whole scenario instead.
Okay.
And
he says break gives me
my third one is using a bronze material.
Okay.
And yeah, so
these stress spots, some of them are normal stress, and you can tell. Okay, good. So yeah, so you can see the magnitude there. You probably have some tensile stress right around the hole, definitely. But you can see most of the stress here is positive, so it's compressive stress. And for your
right overall.
this is for your pulling. Okay, so yeah, it does look different. So you have,
Bro, did you see?
well, I said the tensile stress is higher in this area, while on the other one, the compressive stress is higher.
Yeah.
I was wondering if those three seem okay, or was it like 2 7?
No, that's really fine. Yeah, as long as you have the results, remember the loading snare, they're not meant to be complicated. I mean, some people are going to get really creative with it, but that's fine. But as long as you kind of have it all there and you kind of explain it, so again, the results make sense relative to your description. It sounds like you understand the results, then that's good. Because what some people end up doing is that they just run a simulation and plop the figures in there, and then they don't really, it feels like they don't really understand kind of what the results.
I guess what caused most of like the confusion with me is like because it is a scenario that seems the same. It's just pull, push, and a different material. The description tends to be like a little bit more repetitive.
Yeah, that's okay.
Um,
Yeah, as long as, and sometimes it is, but, as long as I can kind of tell from your description that you kind of understand what's going on, and these results kind of make sense to you, then that's what I'm.
And then for the meshing, I know people did like the refinement,
Yeah.
but I did like, I just individualized the sizing.
Yeah.
That's okay?
Yeah, that you're basically kind of controlling the refinement stuff.
And then what about, because I know a lot of people also did mesh conversion plots. Is that a requirement?
It's not, but mesh conversion plots are a good way to justify the number of elements. Remember, because meshing, you have 3 main things that you have to choose. Choose the mesh size, the mesh order, and the mesh shape. Okay? And so I want to see some justification. Oh. So there's a way that you can justify the number of elements without a convergence plot. But as long as that's addressed in your report, that's fine.
The way I addressed it was like, the applied load's gonna be here. So I made the mesh smaller.
Yeah.
Well, this is mostly gonna be a little bit simpler. That's why I made the mesh larger.
Sure.
That was my only thing. Do you feel like I probably should put the mesh conversion plot?
So that's a good way to go about it too. But now that you have the results, right? Generally, you want to apply a higher mesh density on the places where your stresses are kind of, big, right, or concentrated. So here is good, so here, that's where most of your deformation is concentrated, that's good. You can see here that you have actually have a little bit of stress concentration to the pole. And so that might be something you think about, or, I know you have all your results already, so, maybe just kind of address that in the methodology or in the discussion too. It's like, I hit this mesh and I anticipate that most of the actions would appear, which is where you find the forces that make sense. But, afterward, I saw these, then, maybe I should have had some.
Just some clarification.
I know I'm gonna clarify on the fact that I forgot to put standard gravity.
Oh, actually, for all of these, gravity is probably not that relevant. So these are all fairly small devices, as you do. But, so I think it's okay, but it's good for this.
I also did the hand because I was like, ooh, bank scenario.
Uh-huh.
I was actually gonna ask you, like, you might.
Okay.
I got confused on the last thing, which said tables and figures.
Yeah. Oh, that's just instructions for how you make the table configuration.
Okay, so just setting up like a lab. Okay.
Yeah.
That's fine. I'll just
Yeah.
delete that. And we don't need key figures for it.
No.
Well, if you have time.
Okay, let me get set up first, and then I'll come up.
Also.
Yep.
Interview went well.